Forensic Science Lecture 14-1, The Chemistry of Fire. Fire investigations of arson. Arson presents a complex and difficult circumstances to study for criminologists. And this is due to the fact that it's thoroughly planned by the perpetrator. The perpetrator is not present, typically during the act of the burning, and it's very destructive to all of its surroundings, so that evidence is few and far between. Criminalists are also limited to detecting and identifying relevant chemical materials, reconstructing and identifying the igniter mechanism, and that alone plays a big role in an arson investigation. The other thing is, which makes it even harder, is that there's no test that can determine if the arsonist actually used paper or trash to start the fire, and many of accidental causes can also have caused fires. Faulty wiring, overheating of electric motors, improper cleaning and regulating of heating systems, cigarettes, all of which leave no chemical trace, which makes it even harder for the investigator. But let's talk about what the basic mechanisms of fire is. Fire is a type of oxidation. It's the combustion of oxygen with other substances to produce a new substance. Not all oxidation is associated with fire. We know that when oxygen and iron interact, it creates rust. That is also oxidation, but we're going to focus in on oxidation of fire. Energy is the ability or the potential to do work. Okay, if energy can be in many forms: heat, electricity, mechanical energy, nuclear energy, light energy, chemical energy. But energy in the form of heat is what actually causes fire. The quantity of the heat from a chemical reaction comes from the breaking and the forming of chemical bonds. To break bonds, energy must be absorbed, and then to reform them, they need to be liberated or released. The amount is different for each type of reaction that occurs. When we're looking at fire, we look at the combustion process, and this is when there's a rapid combination of oxygen with another substance. It produces a large amount of heat and light, which we see as flames. All oxidation liberates more energy than required to break the bonds. This is known as an exothermic reaction. Excess liberation of heat and light are known as heat of combustion. We know that some reactions require more energy than is released, and this is known as an endothermic reaction. But for our purposes, we are looking solely at exothermic reactions. So heat is the energy for fires, and there needs to be a minimum temperature in order to start the fire. This is known as the ignition temperature. A lighted match typically is enough to reach this ignition temperature to start the fire, but there are also other sources like electrical discharge, sparks, chemicals that can also create enough heat. But once combustion starts, there's enough heat that's released to continue with the reaction, and the fire will continue to burn either until the oxygen runs out or till the fuel runs out. Another important factor for investigators is the speed of the reaction that they have to understand. The faster the molecules move, the greater the number of collisions, and the faster the rate of the reaction. When factors, or there are many factors that will influence the reaction rate. Two of the most important for investigators for arson is the physical state of the fuel and the fuel temperature. The rate of a chemical reaction increases as temperature rises, and in turn generates more heat and increases the rate of the reaction. If we are looking at the physical state of fuel, fuel will achieve a reaction rate only in the gaseous form. This is the only state where the molecules collide often enough to support a flame. And then fuel temperature. In liquids, temperature must be high enough to vaporize the fuel or put it into a gaseous state. When mixed with oxygen, combustion occurs. The flash point is the lowest temperature liquid gives off vapor that's sufficient enough to support combustion. So once flash point is reached, combustion occurs and the fire starts. If we're talking about a solid, it has to be hot enough to decompose the wood or other solid material into a gaseous product. The chemical breakdown of a solid is known as pyrolysis. And as the heat continues to increase, the pyrolyzed solid fuel, the fire continues to burn, and it will continue to burn as long as the decomposition of the wood or solid is happening. So what we refer to as these reactants come together, we refer to it as the fuel-air mixture. The air or the oxygen and then the sufficient heat are the basic ingredients of a flaming fire. Mixture will only burn within a certain limit. If the fuel concentration is too low or too high, combustion won't occur. So the concentration range between the upper and the lower limits is called the flammable range. We have different types of combustion. We have glowing combustion, which is burning at the surface of a solid fuel, and this is due to the absence of heat high enough to pyrolyze the fuel. And then, so this would be, like burning logs or smoldering embers, or even the end of a cigarette is glowing combustion. Spontaneous combustion results of natural heat producing process in poorly ventilated containers or areas. It's limited in its reaction, and it's rare that accounts for causes of fire. One of the biggest spontaneous combustion situations is with hay that's not well ventilated. Bacteria can cause enough heat to cause combustion to occur within the hay bales. So the requirements to initiate and sustain combustion, there are 3 requirements. A fuel must be present, oxygen must be available in sufficient amounts to combine with the fuel, and then heat must be applied to ignite combustion, and then sufficient heat must be generated to sustain that. And so as long as there's enough fuel and oxygen that's producing the combustion, the heat is going to be sustained. Heat transfers in a number of different ways, and it tends to move from areas of high temperature to regions where there is low temperatures. And so there's 3 mechanisms that investigators have to look for heat transfer. Conduction, which is the movement of heat through a solid object. Solids whose molecules are loosely held have loosely held electrons are good conductors. These are things like metal, and so any parts of a house that contains metal, that heat can be transferred through it to different areas of the structure. Solid whose molecules have electrons that are fully attached are poor conductors. These are things like wood. So in reconstruction, it's important to remember that heat itself may transfer through the metal components to the other location, and any fuel it comes in contact with the conductor may ignite it. A second type of transfer is radiation, and this is the transfer of heat energy by electromagnetic radiation. In a fire, electric or electromagnetic radiation moves in a straight line. So radiant heat plays a role in understanding how the fire can spread through a surface. All surfaces that are facing the fire are exposed to radiant heat and may burst into flames when the ignition temperature is reached. And then convection is the last type of heat transfer that plays a role, and this is the transfer of heat by movement of molecules within a liquid or a gas. So as heat rises, the cold molecules in the air sink, And in a structure fire, the gaseous hot products of combustion expand and move the hot gases to the upper portions of the structure. And this is why in a two-story structure, the flames move upwards. There's a phenomenon that's known as flashover, and this is when all combustible fuels simultaneously ignite and the entire structure is engulfed in flames. And these are in cases of very, very hot fires. This ends lecture 14-1. There's a quiz next class.